Okay. Thank you very much, Neil, for the kind introduction and the invitation for the keynote for this machine learning on graph workshop. I am a year 4 PhD student in computer science, and my research interest, as introduced, is in deep learning for graph structure data. And today's agenda will be on transformers for graph structure data, where I'll be sharing some brief directions about how this research domain is progressing, how transformers for graph structure data has been evolving through the introduction of positional encodings, also what are the different challenges. So this will be the some of the works that I'll be discussing, and the outline will be, first I'll provide a background of the motivation for this particular domain, my interest as well. Then I'll introduce the vanilla graph transformer architecture, which involves one of the key design aspect of positional encoding for graphs. Then we proceed ahead, try to solve some limitations and improve further by decoupling structure and positional representations. After that, I'll introduce some of the bottlenecks of graph neural networks, which motivates further for the development of graph transformers. And it will lead towards a scalable graph transformer framework, which converges many of the ideas in the field that we developed earlier, but also at the same time developed by in the community at large. And finally, I'll outline some of the research challenges and sort of trends for this field as well. So first, for the background. In the recent few years, transformers have become the fundamental building block for many AI advances. We have seen its success in natural language, but also in domains beyond that, in vision, speech, and recently in graphs as well. In graphs, just for a snapshot example, on the Open Graph benchmark, large-scale molecular challenges, if I open up and see the leaderboard as of today, the top 4 models are graph transformers. Some of them could be ensemble, some of them could be engineered in terms of positional encodings, input features, and also some biases for the attention mechanism. But overall, the fundamental building block behind these 4 architectures, even for graphs, are graph transformers. So the transformers have become a very breakthrough architecture in deep learning, and we know that graphs are universal language representing a wide range of data related problems. They're found in domains of chemistry, social networks, and all different domains, for which I would not want to go into detail because of the focus of this workshop. But overall, because the graph structure data, the potential for application is huge, and because the transformers have been very much impactful in the broader domain of deep learning, the motivation is to develop graph transformers and generalized transformers, make it them powerful for also the domain of graphs, which have some different challenges when we compare to the regular domains of images and vision, where the data sets are more regularly structured, unlike graphs in which we have irregular arbitrary structures present in the data sets. So I'll start with how we introduce the vanilla graph transform architectures by doing the generalizations, straightforward generalizations from the transformers architectures in NLP. So we consider 2 design aspects for this to design the vanilla graph transform architecture. The first is the graph sparsity, and second is the positional encodings. So in transformers, we have this multi-head attention mechanism, which is a sort of dynamic way of attending to which different words in a sentences when updating or when generating a word's feature representations. So it becomes a weighted combination of the feature representation of all different words in sentence, and it becomes a way where a model can learn after being trained or pre-trained on a large amount of data. It can learn how to contextualize or aggregate information coming from a words in a particular sentence or in a neighborhood. So as I said, like it's being a state of the art in several applications. And to generalize it to graph domain, we consider 2 key design aspects. First is the graph sparsity. So graph sparsity, I'll try to show what are the differences of consideration in sentences and in graph domain, and what we decide to do with the graph sparsity for graph transformers. So in NLP, the transformers consider some sort of fully connected graph because all for the feature representation of all the words, it attends to all other words in the sentence. So it becomes a sort of fully connected graph. And this choice can be justified for 2 reasons. First, it is difficult to find meaningful sparse connections between words. So we don't know how are the words the first words and the final words are connected, or the first word or second word are connected, what are their weights? So we don't have a very deterministic sparse structure in the NLP sentences. Second, in such data domains, the batch of words that we have, they're usually scalable in memory. So they often contain less than tens or hundreds of words, and they're eventually scalable to consider. It becomes eventually scalable to consider full attention, because when we do quadratic for let's say 1,000 word sentence, if we do 1,000 times 1,000, it's feasible on memory. But in the case of graphs, full attention may not be feasible, because there are several data domains where there are millions and billions of nodes in the graphs, and at the same time graphs have mostly arbitrary connectivity structure, which provides us with the rich source of information about the data that we're dealing with. So sparsity becomes a good inductive bias for generalization. So when we generalize transformers for graphs, we consider graph sparsity and we restrict attention such that it only allows attending to local neighbors, as shown in this figure on the right below. So this is the first design aspect of graph sparsity. Second is the positional encoding. So in NLP, the transformers are mostly supplied with a positional encoding for each word. And what it means is that if we did not have positional encoding in the transformers, we would simply be having a multi-set of words. And with positional encoding, it becomes a way to inform the transformer about the sequential structure that sentences have, the words in the sentences have. So this is a specialized graph structure that if we look from the perspective of graph learning, this sequence is a specialized graph structure, and this structure is provided into the transformer network, or is injected in the transformer network by the use of positional encodings. And apart from transformers, there are other architectures, GNNs, RNNs, they all implicitly consider some kind of positional information as well. But how about graphs, and how should GNN incorporate positional information? So when we have graphs which we are not considering positional information, similar to the scenario with having multi-set of words, in graphs, if we do not have positional encoding, this is like having anonymous nodes. We don't know how a particular node in the graph is spaced out or is located in some notion. So if we would have some positional information, it would ideally make nearby nodes having similar colors, or distant nodes having dissimilar positional features. So what we do is we generalize the positional encoding that was used in the original transformers, and we use a mechanism to encode node positions. We do this by using Laplacian eigenvectors. So how does it generalize the positional encoding used in the transformers is, if we have the sequence of sentences, it appears like a line graph. And if we take a circular line graph, we compute the eigenvectors of the Laplacian of that particular graph, it results in the sinusoidal positional encoding that is used explicitly and in engineered manner in the original transformers. But what if we don't have this sequence, we have any arbitrary graph? So if we take the eigenvectors of the Laplacian, we say that it becomes a way to represent the positional encodings of the nodes, first by the generalization of what is being done in NLP, but second, by the way that it involves, it makes each node, it assigns each node a feature vector, which provides a certain information, which makes it that nearby nodes will have similar features and distant nodes will have dissimilar features. So it will provide some notion of where in my original graph is my node located, a different node located. And this is how it becomes, at the input, we have a feature vector, which is eigenvectors of the Laplacian, and this becomes positional encoding for any arbitrary graph structure. The sinusoidal waves positional encoding we have, it's just for this circular line graph, which represents the special case of sentences. But now we have arbitrary graph structure data, so we can use the eigenvectors of the Laplacian to assign positional encoding. So this is the second key design aspects. And when we combine the graph sparsity and the positional encoding, we have this resultant vanilla graph transformer, where at the input, the positional encoding is generalized to having arbitrary positional encoding for any graph, which are the Laplacian eigenvectors. And second, the multi-head attention is restricted by using graph sparsity. So it only attends for a feature update of a particular word or a particular node, it only attends to those neighbors in which are connected in the first hop. So this is represented by the HJ here, where J is a neighbor of a node I. So this is the straightforward generation, and we have a second extension as well for graph transformer, in a way that we know in the cases of graphs, at many places we can have some information on the edge which are very important. So in the case of molecules, for example, this edge information may represent the types of bonds, single, double, aromatic, etc. In the case of knowledge graphs, for example, it could represent, the edge information could represent the type of links. So when we have this kind of explicit edge information, this can be used to alter or modify the implicit attention scores computed, and we can maintain a parallel module to also update edge information alongside the node information. So these are some of the modification that we do, and this is the very basic straightforward generation, where we try to respect what are the important components of the original transformer and generalize them to the graphs. And when we compare this to in some baseline experiments, what we see is that prior to graph transformer, there was a graph attention network already in around 2017-18. So when we compare graph transformer to graph attention networks, these are significantly faster, and we say that one of the reason behind the performance is that in graph attention network there was no positional encoding considered, so it missed some of the design components of the original transformer. But when we have almost all of the design components from the original transformer for the graph towards the graph transformer, we significantly improve over the graph attention networks. So for the case of zinc, lower is better. For the other two cases, higher is better. And we also have several studies with other different kind of positional encoding, and we observe that the eigenvectors of the graph Laplacian is consistently the better. So this becomes the first vanilla graph transform architecture, after which a lot of works were triggered, and we saw a lot of interest in developing, improving attention, trying to improve how the graph sparsity should be considered, trying to have positional encodings. But I'll try to go slowly and show what are the improvements that we do particularly. So in the previous case of graph transfer, we saw that we simply add the positional encoding at the input with the other contextual node features. But we realized that the positional encoding, that, for example, the eigenvectors of the graph Laplacian, represents a different dynamic of information compared to what we have for node features or node structure features. So what we do is to realize that we may need to process or operate over these two different kinds of features separately. We decouple these two informations, and we learn and update both structural embedding and positional embedding separately at each layer. So this is just to show a pipeline that when we have a message passing GNN and it operates over graphs, it changes the feature vector from one layer to another layer. So in the LSPE architecture, the LSPE here means learnable, structure, and positional encoding. What we do is we separate the feature vector of positional and structure features for each of the node, and we pass them through separate learnable modules. So this is a simple idea of decoupling these two different kinds of information and passing them through similar functionalities of FH and FP, which are basically, you take any graph transformer or any message passing GNN, and you apply similar equation for both the position and structure feature update, but they will have different parameters. So this is a way to decouple and learn these two information separately, and it applies to any message passing neural network or graph transformers for the same reason as well. And it just involves adding a different positional update module, which will have different learnable parameters, and trying to also include this information with the node features at each of the layers. So with this small change, we can apply this to any model that fits into message passing framework. And when we try to use different test examples, so here the SAN, spectral attention network, and graffiti, these two are transformers, other two are message passing GNN. So we show this for a variety of examples, that when we have the learnable, structure, and positional encoding module, which is shown by the tick mark at this column, so consistently, except for one case, consistently the performance of the architecture which learns separately these two different information is improved. So this is a simple idea and an improvement we make further compared to the previous graph transformers. So in the previous graph transformer, we just added the positional encoding at the input, but here we not only just add, but we maintain separate learnable modules to update positional representation as well. Because a positional encoding at the end of the day is a function of the adjacency matrix only, but the node structure features can consist of, let's say, what are the features of a node, if it's a molecule, there could be some atom information, etc. So to separate these two, we have this LSPE, and it shows a very consistent improvement of performance across different architectures for graph transformers and also beyond that. Now we move ahead and we try to find or study some of the bottlenecks of graph neural networks, which will further guide towards improvements of transformers architectures, which have led to the state-of-the-art results in the recent times. So when we consider a computational graph of a graph neural network, which is in the message passing framework, it looks something like this. For a target node, it aggregates features from one hop, and they further aggregate information from their one hop. So it looks something like this. So what happens because of this kind of computational graph? There can be two bottlenecks. One is the smoothing, over smoothing, and second is the over squashing. So first, over smoothing. So if we have a very deep graph convolution network, the features may be over smooth, and it will result in a situation where the embeddings of all the nodes will converge to a similar subspace. So if we see this, the embeddings plotted here, for example graph, what we'll see at the end of the, after gradually moving on from one layer, two layer, and further, the embeddings of the nodes are trying to converge to a similar subspace. So because of the way how the graph convolution network equation is, it leads to a over smoothing. And when we have node classification problem, and there could be so many subclasses, so many classes in the node classification task, it may be difficult to disentangle or distinguish between all different nodes, and we may eventually, in the ideal case, end up having the same embedding. So this is a problem, a bottleneck of the GNNs. And one of the remedies for this is to exploit global graph structure as well, and not only do the local feature aggregation, which may result in the over smoothing. So this is, I'll just take a note of this, and I'll connect it later in the further slides how it's important. So the remedy for this is the exploitation of global graph structure. The second limitation, or the second bottleneck of any message passing GNN is the problem of over squashing. So if we have some task which is long range meaning information propagation between distant hop neighbors are required. So we may require several GNN layers in order to propagate information for long range tasks. And as GNN layers increase, the receptive field of the target node grows exponentially, as shown in this paragraph. And as a result, when feature vectors are aggregated, it may be required for a large amount of messages to be squashed into a single feature vector, because of which there may be some critical information coming from distant neighbors, which may get lost. So for this also, a remedy is to exploit the fully connected graph. And in the work by Alan and Yahav, which principally study this bottleneck, they even try to experiment with fully connected graph at just the final layer, and it solves, or it minimizes the over squashing phenomenon there. So the bottleneck of over smoothing and over squashing, they both somehow hint that we may be required to exploit global graph structure in order to solve these bottlenecks, which has sprung up a different direction of works to have fully connected transformer GNNs, which if we have fully connected transformer GNNs, it naturally solves these two bottlenecks. And but when we have a transformer which just supports some fully connected graphs, it may lose the graph sparsity that I mentioned in the first when designing the vanilla transformers. So in order to incorporate the sparse graph structure information, there are many positional encoding focused innovations in the case of fully connected graph transformers. So I'll just show some examples. I will not be able to cover all the works in the literature, but just to show some examples and try to cluster these works and how how the importance of positional encoding comes in these works. I'll try to just show that. So spectral attention network is one of the work that makes some innovation on the how the Laplacian spectrum is used. We have the graphity, which use diffusion geometry to capture short and long range information, and also they have a bias to the attention where the bias is coming from the diffusion distance, and also there's the work of Graphomer, which uses a combination of centrality, spatial, and edge encoding to improve the node feature update as well as the attention formulations. So what is common in all of these three is all of these three are transformers operating on the fully connected graph, which solves the bottlenecks I mentioned earlier. But at the same time, in order to consider the graph sparse information, it has positional encoding designed in order to abstract or in order to incorporate different levels of information that is required out of the graph structure for the tasks. So positional encoding becomes a function of adjacency matrix, and it applies to all of these works. And when we have fully connected graph transformers, we must make a very careful consideration of positional encoding in order to have the arbitrary graph structure information that's there in the graph data sets. So so this is about how things have evolved. So in the graph transformer, in the vanilla, we had sparse attention following graph attention networks, but slowly we had some improvement on how this positional approach should be used. But when there are some bottlenecks because of these local message passing networks, we can resort to using full connected graphs, but at the same time, we must take care of the sparse graphs in structure information, which is coming from different innovation in positional encodings. And finally, we try to converge all of these different works and present the framework for a powerful and scalable graph transformers. So this is the broader framework, but I'll try to focus and divide in what are the important components. So this is the graph GPS framework. So it is a general, powerful, and scalable graph transformer framework, which consists a module to integrate positional encodings, structure encodings, and at any time, multiple sort of positional and structure encodings can be combined. Sometimes we have seen in empirical practice that if we have some path-based positional encoding, some shortest path-based positional encodings, it may be useful for certain tasks, but may not be useful generally. So these modules at the input, the positional and structure encoding, can be like we can switch it off or switch it on certain kind of methods of positional and structure encodings depending on what are the tasks we have. And then we have the input graph features where we can where we integrate like what are the information, the feature vectors available for the nodes and edges. So this is something that we integrate there. And finally, at the processing layer, we have both message passing neural network as well as global attention. So why both of these are required? The global attention is a way to solve the bottlenecks I mentioned earlier, and the message passing neural network is a way to have some sort of the sparse inductive bias, because these are basically architectures which will integrate local feature vectors when we are updating feature information for the next layer. So this is some sort of hybrid. And MPNN, at MPNN, we may have some bottlenecks which is being solved by the global attention. In the case of global attention, certain information such as edge features may not be integrated directly. So this is done by the message passing neural network. So this is how it takes based of all the words, and this becomes a general framework where different components can be switched off and on while designing the graph transformers. And just trying to shed some more detail, the blueprint, some of the key design components of the blueprint are first the node identification, and where we have positional and structure encodings, which can be chosen based on the task that we are experimenting on. And it's important in order to the positional encoding is also important in order to distinguish between very difficult graph symmetries. So when we have let's say these two example graphs, the two are different, but when we don't have any positional structure encodings, it will be like a situation of anonymous nodes and they will not be distinguished. But when we have the eigenvectors of the Laplacian or some local structure encoding such as random walk, diagonals of k-step random walk. So this will provide different sort of colors which will make it able to separate. So also, in order to make this kind of theoretical improvements, positional and structure encodings are necessary. And in this, like different task-based choices can also be made there. The second is the aggregation. We aggregate the available node information with all these different kind of positional and structure encodings. And finally, we pass through a processing layer, which is a hybrid of a local MPNN as well as a global attention model, which tries to solve the bottlenecks I mentioned earlier, but also takes the best of both of these operation layers on graphs. And when we run this on multiple benchmark data sets, we see consistently the better performance by using GPS. And this is one of the top architectures right now. There's a GPS plus which has been built on top of GPS by introducing some additional positional encodings and structure encodings for molecular settings, and which is the state of the art for the molecular graph challenge on Open Graph benchmark. So this is a general framework which can be many of the moving components can be changed according to the task that we have. And finally, just a smaller benchmark contribution here, that many of the graph benchmarks are small and may not be useful to design graph transform, because if we have molecular tasks which are very small, having graph transformers with powerful positional and structure encoding may be an overkill, and we may not be able to fully realize the impact of graph transformers on this kind of small benchmarks. So with long-range benchmark, we specifically design it to build future graph transformers. And one of the key advantage that we have with graph transformer is that they can intrinsically model long-range dependencies. So this long-range graph benchmark has tasks which are dependent on like the graph size, the nature of task, and the contribution of global graph structure to task. So these are the characterizing factors in these benchmarks. And when we run when we run the MPNNs with few layers, and when we run graph transformer, the graph transformer consistently fare better on all these three tasks. And it also conforms to the theoretical advantage we have with graph transformer, that they can model long-range dependency while having other advantages or motivation from the domains of NLP. In the case of graph, the specific case of modeling long-range dependency is also one of the advantage. And with this data set, this aspect can be also further designed and evaluated. This can become a test bed to evaluate long-range modeling when designing future graph transformers. So just to summarize now, when I'm towards the end of the presentation, to summarize that there has been an increased interest in developing transformers for graphs, and also closing the gap between the transformers in general as well as the graph learning literature, where we had before graph transformer, we had a lot of different designs of GNNs where their only changes were mainly on how the aggregation would be done, some max, mean, or attention, and stuff like that. So now there's a closing of gap between the general transformer and the graph learning architectures. And second, the recent architectures have shown that graph transformers they perform par or better than GNNs on graph learning tasks. Much performance can be attributed to the design of different positional encoding mechanisms, because the attention framework, the self-attention mechanism, and the transformer, there's not much change when we compare to the original vanilla transformers. And finally, we propose a recipe, which was the graph GPS, a general framework, and a benchmark which can lead towards designing further future graph transformer networks. So to conclude, what are some of the challenges and what are some of the research directions in this topic? First is the question of scalability. There are still very large graphs which we are unable to deal with, and sometimes sampling, subgraphing are being done. So this is an open area of how can we do transformers on large graphs which are infeasible to fully fit on memory. The second question is the studies of expressivity, robustness, and generalization. How are the attentional message passing flavor different from convolution and others? And how can we evaluate this in terms of theoretical expressivity, robustness, and out of distribution generalization. So while I have conversations with different researchers, they say that, I mean, it has been found empirically that sometimes on out of distribution, the message passing aggregation still works better than the transformers self-attention. So these kind of questions still remain to determine what are the guarantees of expressivity and generalization as well when we are having transformers performing state-of-the-art on different domains. Next, there's different positional and structure encoding mechanisms that have been emerged for different tasks and for different settings. So what is the universal framework to understand all of these encodings? Because at the end of the day, if we abstract it out mathematically, a positional or structure encoding is some output of a function of adjacency matrix. So that is common in all of these, but still the level of information are different. So what can be a universal framework to understand this? And this is a very important next challenge, is to have pre-trained large models for graphs. What can be that task to work across domains, or if not work across domains, how can we conveniently extend or transfer across domains when we are having foundation or pre-trained large models for this? And finally, questions of domain applications. At different domains, we may have certain specific challenges that we may need to incorporate to do well on those particular tasks. So this is the conclusion of my presentation. There's a very nice visual maze for graph neural networks when dealing with graph transformers. So when we have different problems, we may need to follow some strategies, and this was made by one of my collaborators, Dominic. First, like, we do some MPNLs. It does some sort of walk and look around and aggregate information. But there are some problems such as over smoothing, over squashing. So when we try to have some coloring, we try to squeeze some narrow path, we may use some map, which is a positional encodings, or some other works along this side. We may need to do some wall destruction. So there are some works such as graph rewiring, which solve some of the bottlenecks that may come from narrow bridges in graphs. And finally, we can use wings. So when we have fully connected graph transformers, it allows each of the node to be connected to each other node, so we don't have many of the bottlenecks. So this is just to conclude on how we can follow some first principles when working on graph transformers. And thank you to all my collaborators in all of these works. If there are any questions, I'll be happy to take.
Thanks, Vijay.
Thank you.
All right. Do we have any questions? I will start because I have several. Firstly, yeah, thanks for the really expository overview about both your work and others. I think the first question I have here, and this is maybe back to your motivations, of bringing the transform architecture from NLP to graphs, is that there's a handful of works that we in the graph machine learning community are familiar with that kind of now show how similar transformers are to graph neural networks and how deeply connected they are. And this is kind of an idea of bringing a concept from NLP into the graph machine learning domain. Now, some of the stuff you talked about regarding the graph machine learning domain, we have kind of explicit sparsity constraints or considerations that don't exist in the native language modeling domains or NLP domains. So can you, I'm not sure if you're aware of any work that's ongoing that actually tries to adopt the advantages, for example, that sparsity imposes in the graph domain and bring it back to transformers in the NLP domain.
Yeah, so I think it's a very nice consideration, like to just move back into the domain of NLP and try to apply some sparsity advantage that we are getting in the graphs. I'm not aware of a very explicit work that do that. One of the reason for that may be that we may not have sparse connections that we have in graph in the case of sentences. There could be some of the ways to show that NLP sentences have sparse patterns, such as the syntactic structures that used to have used to be present in traditional NLP, but I'm not sure whether they're being used recently as or not. But I think one of the reasons why this is not enforced much is the way how it provides a dynamic way of looking which words to attend to when I'm developing a feature representation of a particular word. So when we have a multi-head attention architecture, that becomes a very dynamic way of doing that. But in the case of graph, we want to have that dynamic, but at the same time, we want to enforce constraints that is present in the case of graph structure, sparse graph structure information. So I'm not sure if any, I'm not aware of any of the work that tries to bring back these advantages from the graph machine learning community to the NLP.
Got it. Thank you. Any other questions? Okay, I can keep going. I have a few others. So, yeah, so I guess a follow-up to that question is, you know, you kind of explicitly, we just explicitly talked about these differences between, I guess, like all pairs, multi-headed attention that you have in transformers for NLP, and then, you know, kind of like not quite all pairs, but a, you know, masked kind of a multi-headed attention that we have in the, you know, in the graph domain or in the graph transformer setup, where we're trying to impose, you know, attention specific, conditionally specific to the graph structure. Are there, in your observation, I mean, we could of course like take this, like the choice to actually do the masked attention in the graph domain or in the graph transformer domain is a choice. Like we could actually drop this mask entirely and do all pairs attention anyway, like completely throwing sparsity out the window. I'm curious if you have any anecdotal observations of whether this has been tried and whether this is a good idea. I'm not sure, you know, in some cases, whether the graph structure and the sparsity that we're given is indeed like something we should leverage or should not leverage.
Yeah, so this is a nice question, and I want to say that like this has already been tried by removing the mask and simply doing full attention similar to NLP. But when we do that, we have to compensate for the loss that we are making in the graph sparsity, and this is what was shown in one of the slides here. So I'll just quickly scroll back to here. So when we have this transformers which are fully connected. If we are having fully connected transformers, it means exactly the same thing that you mentioned, that we remove the mask for a restricted attention based on the graph sparsity. So when we remove this restriction and have full attention, we must compensate for the graph structure information that we are losing because of this setting. And for this, we have different positional encoding based designs. So for example, I'll say, for example, of graph-former, just for example. So in this case, if there's a graph of 20 nodes, let's say, it doesn't have this mask. It does attention of in a fully connected 20 node graph. But in order to encode what are the degree centrality, it has degree centrality positional encoding. Then it has a spatial encoding, which is based on shortest path distances, and then there is an edge encoding as well, which is some sort of bias that it provides to the attention. So with the combination of centrality, spatial, and edge encoding, it is trying to compensate for the information that was present in the original graph transformer, graph sparse structure. So yes, this is being tried eventually, exactly. And when we do fully connected graph transformer, we remove this mask. We solve these bottlenecks as well. So these bottlenecks result because of the way the computational graph is based on the local graph structure. So when we remove this mask, as you mentioned, we let go of this computational graph based on the local structure, and we address these bottlenecks. But at the same time, when we want to incorporate the graph structure information, we must design and some positional encoding which incorporates that to the network. Yeah.
Got it. Thanks, Vijay.
Thank you.
All right, I think we have time for maybe one more short question if there is one, but if not, we can move along because none of my questions are short. No? All right.
Okay.
Let's thank our speaker again.
Thank you very much, Neil. Thank you.